Owners of 9 Rimac Neveras in the United States received an extraordinary warning. Do not drive your car. Imagine spending $2 million on one of the fastest machines ever created. Only to be told that it may not be safe to leave your garage. Not because its massive battery had failed, not because one of its 4 electric motors had stopped working, but because one low-voltage cable could move out of position, damage its insulation, short against the carbon fiber structure, and become hot enough to melt, potentially increasing the risk of fire. This is a hypercar with 1,914 horsepower, a car capable of reaching highway speed before your brain has fully processed the launch. So how could one ordinary cable threaten one of the most advanced cars ever built, and how did Rimac fail to catch it? The answer is not hidden inside experimental battery chemistry. It is much more ordinary, and that is exactly what makes it so important. The component at the center of the recall was the C19 low-voltage cable. According to the official safety filing, it may not have been assembled or tightened correctly. That could allow it to move away from its intended position during normal driving. And once that happens, a small problem can begin to grow. Movement can damage the protective insulation. The exposed cable can then contact the carbon fiber monocoque, creating a high-resistance short circuit. Electrical resistance creates heat, the temperature rises, the cable begins to melt, and the risk of fire increases. The warning signs could be as simple as a strange smell or smoke. Think about that for a moment. A machine engineered to survive brutal acceleration, extreme heat, and enormous electrical loads could still be threatened by a cable no thicker than your finger. That is why Rimac did not tell owners to book a repair whenever it was convenient. It told them to stop driving until the car had been inspected. Only 9 American Neveras were included in the recall, and Rimac estimated that perhaps just 10% of them actually contained the defect, potentially only one car. So why react so aggressively? Because when the possible result is fire, one car is already too many. But why does a hypercar with a battery operating at hundreds of volts need a low-voltage cable at all? An electric hypercar does not run on one electrical system. The main high-voltage battery provides the muscle. It stores the energy that feeds the motors and launches the Nevera forward with almost 2,000 horsepower, but modern cars also need lower voltage systems. They support computers, control units, communication networks, and auxiliary equipment. In simple terms, the high-voltage battery provides the force. The lower voltage systems help the car wake up, think, and communicate, and that creates a strange contradiction. The Nevera can produce almost 2,000 horsepower, but it still depends on small electrical components working perfectly. The official recall does not publicly explain the exact job of the C19 cable, so claiming that it controlled one specific function would be dishonest. But the danger is clear. Incorrect position, damaged insulation, short circuit, heat, melting, possible fire, a basic physical sequence hidden inside an extraordinarily complicated machine. And that contrast becomes even more surprising when you understand what Rimac actually built. The Nevera uses 4 electric motors, one for each wheel. Together, they produce 1,914 horsepower and 2,340 newton-meters of torque. 0 to 60 miles per hour takes just 1.74 seconds. Press the accelerator, and the car reaches highway speed before your brain has fully understood what is happening. Its top speed is 412 kilometers per hour. At that speed, the Nevera can travel more than the length of a football field in a single second. But the real engineering challenge sits inside the chassis. A 120 kilowatt-hour battery containing 6,960 individual cells. It is liquid-cooled. It can deliver around 1.4 megawatts of power, and it is shaped like the letter H, allowing the driver and passenger to sit low inside the car. The battery is not simply carried by the structure, it is part of the structure, adding 37% to the stiffness of the carbon fiber monocoque. Rimac developed a battery capable of delivering almost 2,000 horsepower while also helping make the entire car stronger. It created 4-motor torque control, advanced cooling, brake-by-wire, and regenerative braking. Its software can continuously adjust the power sent to each wheel. The Nevera can calculate, react, and redistribute torque faster than any human driver ever could, yet none of those revolutionary systems caused the recall. The problem was physical. A cable may not have stayed where it was supposed to stay. So how could Rimac test the Nevera so extensively and still miss something so simple? Before the Nevera reached customers, Rimac spent 4 years completing its crash testing program. The company ran thousands of digital simulations. It performed 45 physical crash tests, and 9 complete vehicles were destroyed. The car was hit from the front, the side, and the rear. Its carbon structure was tested against forces most Nevera owners will never experience. So why did those tests not reveal the cable problem? Because crash testing and production quality are not the same challenge. Crash testing asks, can this design protect the battery and its occupants during an extreme impact? Production quality asks, can every component be installed correctly on every car every single time? One tests engineering, the other tests repeatability. And repeatability is where even brilliant engineering can become vulnerable. A component can be perfectly designed and still become dangerous if it is routed incorrectly, given too little clearance, or tightened in the wrong way. That is the uncomfortable truth. A hypercar does not depend only on revolutionary ideas, it also depends on thousands of ordinary actions being completed perfectly. Every bolt, every connector, every cable, every time. Low-volume hypercars make that challenge unusual. The Nevera was limited to only 150 examples. Each car is extremely complex and built in tiny numbers. That allows enormous attention to detail, but it gives Rimac far less production data than a company building hundreds of thousands of vehicles. In a mass-produced car, a rare defect can create thousands of affected examples. In a hypercar, the same problem may appear only once, and that can make it much harder to detect before a customer discovers it. But there is a limit to what we know. The public filing explains what could fail and why it was dangerous. It does not publish a complete root cause analysis. We do not know whether the issue began with a procedure, a fastener, a tolerance, human error, or several small factors combined. So the honest answer is simple. We know what could happen. We know why it was dangerous, but we do not know every internal detail of how it escaped. What we can judge is how Rimac reacted after discovering it. Rimac opened an internal investigation in October 2024. Within days, its product and safety committee decided to issue a recall. Affected owners were contacted. Their cars would receive a visual inspection. If the cable showed the defect, Rimac would repair it free of charge. The company would also cover transportation to and from an authorized service facility. But the most important instruction remained the simplest. Do not drive the vehicle until the inspection is complete. For a company selling a $2 million technological showcase, that message is painful. Imagine owning a car built to break records and being told that the safest place for it is standing still. But minimizing the danger would have been far worse. A recall does not automatically mean that a car is badly engineered. The real test begins after the defect is found. Does the manufacturer acknowledge it? Does it communicate clearly? Does it remove the risk? And does it prevent the same problem from happening again? Rimac treated the potential fire risk seriously, even though only 9 American cars were included, and perhaps only 1 actually contained the defect. That helps protect the company, but it does not remove the larger lesson. The public filing does not reveal every production change Rimac made afterward, but the engineering lesson is difficult to ignore. Cable routing matters, clearance matters, fastener torque matters, inspection matters. The Nevera can control 4 motors independently. It can deliver 1.4 megawatts from its battery. It can accelerate faster than almost anything on the road. While also trying to become the fastest production cars in history. They are pushing into territory where there is no century of experience. Manufacturers are still learning where unexpected weaknesses can hide, and sometimes they are not hidden inside the most advanced technology. Sometimes they are hidden inside one ordinary cable. So did this recall prove that the Nevera is a failure? No. Its records still exist, its battery is still extraordinary, and its acceleration is still almost impossible to understand until you experience it. But the recall destroyed one illusion: the belief that advanced technology can eliminate ordinary mistakes. Rimac solved problems that once seemed impossible: how to produce almost 2,000 horsepower using electricity, how to control 4 wheels independently, how to reach 60 miles per hour in less than 2 seconds, how to turn a battery into part of the car's structure. But in the end, the Nevera was not stopped by physics. It was not stopped by battery technology. It was not stopped by 4 electric motors. It was stopped by 1 cable, a a cable that may not have stayed in the correct position. And that might be the most important lesson of the Nevera, because building something fast is difficult. Building something revolutionary is even harder, but building it perfectly, every single time, may be the greatest engineering challenge of all. Would this recall make you trust Rimac less? Or does the company's decision to stop the cars and repair them make you trust it more? Welcome to the Lux Driven. Don't forget to subscribe, because the next episode might be even more unbelievable. Thank you for watching.